Let's look at theorem 9.4, children. The theorem says the line drawn through the center of a circle to bisect the chord is perpendicular to the chord. It's the converse of the previous theorem which said a perpendicular from the center to the chord bisects the chord, right? So here what we are given, we are told that the line which will be joining the center of the circle to the midpoint of the chord, or the line drawn from the center of the circle to bisect the chord, both mean the same, will be perpendicular to the chord. Perpendicular means what? It will make a 90-degree angle. So let's look at a circle. Again, please assume this to be a circle. Okay. If we have a circle over here, please assume this to be a circle, and we have a chord AB. We have the center O, and we'll call the chord as AB. We have a line segment, say OP, which is bisecting AB. Means we are told that AP is equal to PB. Now we want to prove that OP is perpendicular to PB. OP is perpendicular to AB. So that means we want to prove that OPA and OPB are 90 each. Right? Then it will be perpendicular. So what is given to us? Which is the circle that we are talking about? In circle with center O and radius OA, what is told? AP is equals to PB. Bracket, what we can write? OP bisects AB. OP bisects AB. We are told that AP is equal to PB, which means that OP bisects AB. If so, we have to prove that OP is perpendicular to AB. And to prove it is perpendicular, we'll prove that angle OPA, or for that matter OPB, will be 90. If it is 90, then we know it is perpendicular. We'll join OA, we'll join OB, because the angles are part of these two triangles. We'll again try to prove the angle OPA is part of triangle OPA. Angle OPB is part of triangle OPB. So we'll try to first prove them congruent. So we'll write here, in triangle OPA and triangle OPB, what are the equal parts, children, that we see? We'll get three equal parts. First is given to us, AP is equal to PB. It is given to us. We have not thought of it at all. It's given as it is, we've written. Second that we see is OP is the common side. OP is equal to OP common side. Which is the third one? Very good. OA is equal to OB, and why so? Because they are radii of the same circle. Radii of the same circle are equal. So, can we say that triangle OPA is congruent to triangle OPB? By which test? We've taken all the three sides, so we have SSS test, right? We'll write this is true by SSS test. And because these two triangles are congruent, we can say that angle OPA is equal to angle OPB. And what is the reason for it? They form corresponding parts of congruent triangles. Now, let us call that these two angles are X. Measure is X. So, what do we know? In the second part, let us write angle OPA plus angle OPB will be how much, children? OPA is this. OPB is this. If we add them, we are going to get 180. Very good. Why? The reason is going to be angles in a linear pair. Angles in a linear pair. We've taken OPA as X. OPB is also X, is 180. 2X is 180. So can we write X is 90? What did we get? We got, therefore, angle OPA equals to angle OPB, which we wrote as X is 90. And therefore, can we write that OP is perpendicular to AB? Yes, we can, because the angle is 90. I hope you have understood this. It was simple. It was converse of the previous theorem. Previous theorem we said perpendicular from the center of the circle to the chord will bisect the chord. Here we are saying a line segment which bisects the chord and is passing through the center is perpendicular to the chord. Right? So now let's look at the next theorem. The next theorem is there is one and only one circle passing through three given non-collinear points. Here you don't need to prove it, you just need to remember. And what does this actually mean? Suppose we have 3 points. Anywhere you can take, the only condition is they are non-collinear. I've taken point A, B, and let us take point C. Okay. I'm taking point C, somewhere here. Okay. These are my 3 points. Now we want to check, will there be a circle that can pass through all the 3 points, right? So which property do you think is going to help us to prove it? The previous theorem that we did can help us over here. Let's try. Let's try. Look at the 3 points. Which are the 3 points A, B, C? If we are assuming that A, B, C will lie on the circle, then AB becomes a chord. Likewise, BC is another chord and AC is the third chord. We know that if we have perpendicular bisectors of the chord, they will pass through the center. So if we do construction of perpendicular bisectors, which will be something like this, of all the 3, the point that you get on intersection of 2 perpendicular bisectors of any 2 sides will be called as the center. What are you supposed to measure? We are supposed to measure the distance OA, because if we are assuming O to be the center, then A is on the circle. A line segment which joins a point on the circle with the center is the radius. OC should also be the radius and OB should also be the radius. If we take the measure and if we construct a circle, our circle will pass through all the 3 points. This is not the perfect circle, children, but if you try it, you will get the exact measure. Okay. So this is one way of proving that if we have 3 non-collinear points, this property is true for only non-collinear points. If I give you 3 points which are collinear, can one circle pass through it? No, because at a time there will be only 2 points which will lie on the circle, isn't it? At a time we are going to have only 2 points through which the circle can pass. Third point will either lie inside, or if I take these 2 points, then A will lie outside, right? So what you have to remember, that the 3 points are non-collinear. I hope you've got this. Let's move on to the next question, next theorem. What does the theorem say? It says equal chords of a circle or of equal circles. Now over here, what we need to remember, what we need to understand is or of equal circles. We'll come to it later. We'll just read the entire statement and come back. Equal chords of a circle are equidistant from the center. New word, equidistant, from the center of the circle. Now, what first? Understand what is equal circles. When are 2 circles said to be equal? When their radii are equal. If their radius are equal, then we say the 2 circles are equal, because to measure a circle, there is only one dimension, which is the radius, right? Now, equidistant. What is equidistant? Equidistance is nothing but equal distance. Equal distance. It is true for when you're taking the chords in the same circle, or you're taking chords in 2 different circles but which are equal. Please assume this to be a circle. I know it's not accurate, but please assume it to be a circle. Now, if this is the center of the circle, we have 2 equal chords. So let us construct 2 equal chords. Let me say AB is one chord and let me call PQ as the other chord. We are telling that these 2 chords are equal. AB is equal to PQ. Okay. Equal chords of a circle are equidistant from the center. They are distance from the center. They are distance from the center. So this will be the first distance. Let me call it as OL. When we say distance, children, we are always talking about the perpendicular distance. So OL is the perpendicular distance of chord AB from center O. And let us assume that OM is another perpendicular from the center to the chord PQ. We want to show if AB is equal to PQ, then their distance from the center, their distance from the center OL and OM are also equal. So what is given to us? We are given in circle with center O and radius OA or OB or OQ or OP, whichever you want to take. What is given to us? OL is perpendicular to AB. OM is perpendicular to PQ. We are also given that chord AB is equal to chord PQ. Okay. And what we want to prove, that these 2 equal chords are going to be equidistant from the center. That means their distance from the center is equal. Distance of chord AB from the center is OL and distance of chord PQ from the center is OM. This is what we want to prove. Is the question, is the statement of the theorem understood? Now again, if we take the entire triangle OAB, assume this, if we are taking the entire triangle AOB, will it help us? We want to prove that OL. If I take the entire triangle, OL lies inside, so that will not help me. So if I want OL, children, then we need either of the triangle, sorry. Either I can take BOL and say QOM, or any the other triangle POM. We prove that these two triangles are congruent. I'll get OL is equal to OM by CPCT, because they'll form the corresponding parts of congruent triangles. I hope you understood why I've chosen these two. See, what you're supposed to do from AB, when OL is perpendicular to AB, it will make two triangles, OLA or OLB. You can choose one from here, any one. OMQ, OMP, you choose any one from here. I've chosen these two, and I'm going to try to prove that they are congruent. If I directly start, children, let us mark in the figure what is equal. Angle 1 is equal to angle 2. Why so? Because each is 90. OB is equal to OQ, radii of the same circle. Do we have anything else? No, directly we do not have. So first, let us look at the other information. What is given to us? OL is perpendicular to AB. OL is perpendicular to chord AB. And we just did the theorem where we said perpendicular from the center to the chord bisects the chord. Right? So first things first, we will write here, in triangle or in circle, sorry, in circle with center O and radius OA, first thing, OL is perpendicular to chord AB. This implies what? This implies that AL is equals to LB is equals to half AB. Why? Because from theorem we know perpendicular from the center of the circle to the chord bisects the chord. It is going to divide the chord into two equal parts. Similarly, we can write for OM. OM is perpendicular to chord PQ. This means PM is equals to MQ is equals to half PQ. For both, what reason can we write? Perpendicular from the center of the circle. Please don't get into the habit of writing theorem number. You should remember the statement of the theorem. Perpendicular from the center of the circle to the chord bisects the chord. Now, what else is given to us? We are also given that the two chords are equal. Chord AB is equal to chord PQ. So we know Euclid Baba has taught us in chapter 5 that halves of equals are equals. Halves of equals will be equal. We've learned this from Euclid's the chapter Introduction to Euclid Geometry. Half of AB is AL and LB. Which one is going to be helpful to us? Since we have chosen this triangle, I'm going to take half of AB as LB, and since I've chosen OMQ, I'll take half of PQ as MQ. Right? So we got this also now. And now we start writing for triangle. Now next statement would be in triangle. Which are the triangles that we have selected? OLB and triangle OMQ. If we write the three equal parts, what are we going to get? We get OL is equals to OM. Why? It is given to us. I'm sorry, it's not given to us. This is what we have to prove. Big blunder. Sorry. This is what we want to prove. What is given to us then? We are given that angle 1 is equal to angle 2 because each is 90. Next, what is given to us? We are given that OB is equals to OQ, radii of the same circle. And third, we just now proved that LB is equals to QM, proved above. Question mark I put because I have less space. You can write over there in detail. It is radii of the same circle. So what do we get here? We get triangle OLB is congruent to triangle OMQ. By which test, children? Again, I told you, do we have any ASS test? No, we do not have any ASS. So which is the test? Right hypotenuse side. Which is the test? RHS. And because the two triangles are congruent, can we say OL is equals to OM? Yes, because they form corresponding parts of congruent triangles, and hence we have proved it. I hope, children, you all have understood this theorem.